His last name is also Costa.
Yeah. So there are two making groups of pastas. There are Italian pastas, right? Yeah, I'm the Italian Irish, but they're from the Irish. They're the Portuguese pastas. And then there are the being short in between the ground one and three two with the combination of those types of innovations. Yes. One would be like we like anytime when I was a kid.
Okay, so good morning and welcome back to this workshop on artificial intelligence for medical image analysis. So in this morning we have a series of talks. Actually we have 3 talks and we have 2 distinguished speakers. So before that I'd like to introduce you the speakers. So the first one is Professor Anthony Costa. Okay. So he got his PhD in chemistry at Purdue University. And then he worked as a postdoc in Northwestern in chemistry and also biomedical engineering. And he also worked in some physical simulations. So as you can see, he will be talking about some simulation from physics to medicine. After postdoc, he moved to Icahn School of Medicine at Mount Sinai in New York City. It's 西奈山医学院跟医院。So he is also a computational scientist there, and currently, actually, he is also director of neurosurgery simulation code. So he actually developed a lot of very interesting and very impressive tools. I'm sure he will talk some of them in this talk. In addition to academia works, he's actually co-founding a startup. So the company is doing some kind of medical devices and embedded with some software and some very cool methods. So this is Professor Anthony Costa. And our second speaker is Dr. Eric Omen. So Eric has actually got his bachelor degrees in mathematics, focus on differential geometrics. So it's very math oriented. And then he got his he went to medical school in Georgetown. And right now he is a neurosurgery in Mount Sinai Hospital. So he redo this kind of operation. But he is not only a doctor, is Actually, he quit from the surgery to work in Google as a software engineering for 1 year, so something like that. So it's kind of very impressive, very interdisciplinary. And again, he also co-founded a company working in some medical image analysis. So as you can see, we have very two distinguished speakers, and I'm sure in the next 3 hours we'll be enjoying their talks. So please join me to welcome Anthony. So.
Well, thank you very much, Professor Wong, for the kind introduction. It's really my great honor to be here today. I'm really thrilled to have the chance to visit Taipei and Taiwan as well. So when I wrote this abstract, after I wrote this abstract for this talk and started putting this together, I realized that I really never tried to combine some of the things that I'd done in my life before I worked in the medical discipline and what we do now into one sort of cohesive story. So this is my attempt at that. So you all get to be sort of guinea pigs for my attempt to put these kinds of things together. So I started, I did my PhD in chemistry, really in computational chemistry, and then did some theoretical physics work, also primarily in computation. And so when I think about simulation, that's how I got into medicine, I think about simulation, at least historically, quite differently. To me, simulation looks something like this, where we're producing very pretty pictures and solving some kind of pseudo equations. And so this was work actually that I did during my PhD, which was about droplet thin film collisions on surfaces. And the motivation for this kind of work came from things like understanding, in this case, an ambient ionization method in mass spectrometry. I happened to be working in a local chemistry group at that time. And so we had basic questions about the mechanism of some of these ionization techniques, and we used some kind of theory to figure that out. In this case, we were questioning whether or not there was an electrostatic contribution to what was going on. At the surface here, this is, if you're not familiar with this is an ambient ionization method, and the cool thing about this is you spray really tiny droplets, you can't really feel them, you can put your finger in front of this ionizer, and you pick up some stuff in free air, and you put that into a mass spectrometer, and you can get all sorts of nice complex chemical information. Very different than medical applications, but nonetheless quite interesting. We did solve some basic challenges in terms of the mechanism of this, but of course, one of the nice things about simulation in general is that you make really pretty pictures, and everyone likes to work those. So this is an example of one of those droplet thin film collision simulations that we did, and then we look at statistics of all of the particles that are actually ejected from the surface and correlated those some laser interferometry that we did in the lab and saw quite nice agreement. And so we used that to establish a theory of how this technique works. Other kinds of things that I've been motivated in simulation before to work on prior to what I've been working on recently in medicine, again, come from, or at least motivated from the analytical chemistry world. This was an observation that was really interesting that I got just absolutely fascinated with and spent maybe 5 years of my life trying to figure out. So this is a mass spectrum. If you're not familiar with mass spectrums, it doesn't really matter. What matters is over here we have this really big peak, and that big peak corresponds to some gas phase chemical species. In this case, it's an amino acid. It happens to be serine, which is one of the 20 standard amino acids. That for some reason, when we do a whole bunch of things experimentally, is uniquely stable, and you see this in this mass spectrum is just dominating everything else that's going on here. And for some reason, serine in the gas phase likes to cluster into groups of 8. And in and of itself, maybe that's not the most interesting thing in the world. But then if you look at all the rest of the amino acids in the gas phase, and you see all these down here, and the clusters that they like to form, and you look at the relative probability of clusters in the gas phase being observed, you see that serine is pretty unique. There's one other blip right here, but that turns out to be a artifact. And so we tried to understand this from a theoretical standpoint. The reason this was especially interesting was because, as it turns out, serine likes to cluster only in homochiral groups. And as some of you may know, if you have some biology background, I think I'm right in saying all living things have chiral amino acids and sugars. We have left-handed sugars and we have left-handed amino acids and right-handed sugars. And there's a great debate in a lot of the literature these days, and it continues to this day, about what the mechanism of that process was. Why do we have only right and left-handed sugars and proteins? And as it turns out, this was a mechanism, a proposed mechanism for chiral enrichment. So we could end up in a system in the prebiotic early Earth or extraterrestrial Earth even, that are responsible for enriching one kind of amino acid over another. And we looked at all sorts of kinds of simulations to figure this out. So we looked at energy landscape theory. We did these kinds of both quantum and statistical, as well as classical simulations of groups of amino acids. In this case, these are string tetramers. And we used kinetic simulations as well as molecular dynamic simulations to figure out what the energy landscape of these are and what the most likely conformal state of these things are in the gas phase, and establish some basic theory about why serine clusters the way that it does. Wrote a paper about it, and it's still hotly debated. We certainly have not solved the problem of homochirogenesis. But what I really want to start with in terms of simulation, what I'll try to get from where we are to what's going on in medicine is in non-equilibrium systems. And this is what I did during my time at Northwestern. It's really actually a great pleasure to talk about this again, because I don't get to talk about this work as much as I'd like to. But the thing that I did, during my postdoc was really learn how it was important to know how to do compute. So although there's a lot of physics and chemistry involved in this, fundamentally we recognized a very fundamental computational problem and spent many years trying to solve it with software. And so if you're not familiar with non-equilibrium systems, I'm sure many of you are. This is a particularly topical example of a non-equilibrium system on planet Earth in the year 2017. There've been a lot of these. It's a hurricane approaching Florida. I don't know if this is a picture, actually I forget where I got this from, but it's a hurricane approaching Florida. This is a very typical non-equilibrium system. And what do we mean by non-equilibrium system? So we have this whole theory called thermodynamics and statistical mechanics and chemistry and physics that tell us certain things as long as we meet some criteria, and systems are in what we call equilibrium. In general, when we are in equilibrium, we use the term thermodynamic limit, meaning that all the quantities that we can measure about the system are infinite or interchangeable between time and space. So if I measure the temperature in this, if this room is in equilibrium, and I'm over there in that corner and I measure the temperature, and I measure that temperature over a long period of time, and then I go over to this corner and I do the same thing, I should probably get the same answer, right? It also has the property of having no input, so there's no work done on the system. There's no heat source or other kinds of driving mechanism. And it also has no dissipation, so it's not dissipating energy to its surroundings. In contrast, in a non-equilibrium system, we have work, input, and heat. And we don't necessarily know how to measure things. There's not necessarily a definition of a temperature or even a number of particles or a volume for a non-equilibrium system. And then these systems have the property of not only having inputs of work, but also having outputs of dissipation. And so if you think back to that example of the hurricane, that should be pretty obvious. You have sun beating down on the ocean warms, you have constant input of energy into the hurricane, and it dissipates in energy in a fairly violent fashion when it comes to a shore and causes significant destruction. The classical equilibrium case is this. You have a protein and water. You do a molecular dynamic simulation of this. You couple this to some fictitious internal bath, which fixes the temperature of the system. And you just watch it evolve with time, and you collect statistics along the way. And if you collect enough statistics, you can compute all sorts of nice thermodynamic properties, like how the protein likes to bind to maybe a drug, which is an active area of research, of course. In contrast, if I put a hurricane in a box, if you set aside the fact that this is computationally and otherwise completely ridiculous, but just from a conceptual standpoint, if you put a hurricane in a box and I ask you, what do I set the temperature to? That question doesn't make any sense, right? Because if I set the temperature to the whole system, all of a sudden I destroy the hurricane. So what simulation do we even do to understand the statistical mechanics and the thermodynamics of non-equilibrium systems? This is my favorite, really simple example of this. This is a cool little system. What you're going to see is that some hand's going to come in and they're going to shake this thing, and the particles are going to disperse, and then they're going to come back, and then they're going to start spinning again, and they're going to reassemble. This is from work that was at Northwestern when I was there by an experimental group. It's a deceptively simple experiment, but it's actually quite powerful in terms of our understanding of non-equilibrium phenomena. What you don't see is underneath this well plate is a magnet spinning at 50,000 RPMs, and these little balls, maybe in the back, they look like nice spherical objects, but in fact they are not quite spherical. They have a little tail on them, and as they spin off vortices in the fluid, and they set up these gradients that keep the particles separated from each other, but also as they assemble, they assemble in specific ways, and they assemble in different ways every single time they reassemble. So this is an example of a non-equilibrium self-assembly that can't exist and can't be set up or maintained without a constant input of work. So that's quite cool. Our system was even simpler than that. It was a set of particles in a bath. Here we have a bunch of red particles, which are these tagged particles that we're going to cause to assemble some way. And then we're going to do something to the system. We're going to change something about it. And these particles are then going to be driven to assemble each other in the bath. And as they do that, they're going to dissipate a bunch of energy, which is going to be contained in the surrounding bath particles, which are these nice clear ones as opposed to the red ones. What we're interested in this case is, instead of understanding the statistics of, say, a protein in water, is instead understanding the transition from equilibrium ensemble A through some change to another equilibrium ensemble. So the set of all possible states of the equilibrium of the disassembled system. Then we turn something, we change something, all of a sudden the system is driven to another state. And we want to look at all possible trajectories between ensemble A and ensemble B. This is how we do that. This is, if you've never done any molecular dynamics simulations, this is like MD 101. The actual MD here is ridiculously simple. You can write it all in any language in about 50 lines of code. It really is very easy. We use a Lennard-Jones potential. This is the potential energy function. It's a function of the distance between particles. These are pairwise interactions. So at each point, we compute all the interactions between particle 1 and all the other particles in the system. So it's order n squared. And we do that for all those particles. And then at some time, we take this parameterization of this potential energy function, and we drop the number. And we do this iteratively over and over and over again to look at thousands and thousands of trajectories of the self-assembly process. As you deepen the well, all of a sudden these particles are driven to assemble. As they assemble, they take all that potential energy and they convert it to kinetic energy. They dissipate that energy to the bath, which is what all of these clear particles are. And when you do that, you get some very nice, if quite predictable results. This is the temperature of the bath as a function of time. This is the average change in the kinetic energy of the bath, or the average change in the temperature of the bath. And so you see that after you do this, all of a sudden the temperature of the bath raises, which is not particularly surprising. If you make bigger changes in that potential energy function, the temperature of the bath goes up even more, and so on and so forth. If you then look at the kinetic energy of the system particles, they actually don't change very much at all, which is understandable. They have dissipated their energy to the bath, and that's what contains all this excess kinetic energy. So we want to look at trajectories. We want to understand the statistics of trajectories between the non-assembled and the assembled state. And so what we do is we borrow some work from probably a number of people here, or at least the dynamic systems crowd, and we look at the collection of all the off and off exponents in the system. This is where our MD simulations go from being quite straightforward to being quite complex. Of course, the off and off exponent is defined as just the log of the rate of the distance between two trajectories in phase space. And so we start with two infinitesimally close trajectories, and then we propagate those in time. Assuming we have just a 2D system here, we look at those and we compute the ratio and take the log, and we take one of the first time, and that's your off and off exponent. Right? So positive exponents, I know I'm speaking to the choir here probably, but positive exponents, trajectories are diverging. Usually that indicates a lack of predictability of the system. We also call that chaos, right? And in negative exponents, trajectories converge. Two phase points that are very far away from each other converge together. That's an extremely predictable system. And so we call that non-chaotic or more predictable. Again, I think this audience is quite familiar with these kinds of things, but when I give this talk to more lay audiences, I sort of give the example of assuming, let's say you're in a river, this is some gorge in the US, and you take a bunch of ping pong balls and you throw them all into the river and you watch how they separate, and they compute the rates of how they're separating. That's basically what we're doing in this case. Instead, we're doing this at each time, at every time step in the entire simulation for all 2dn, where d is the dimensionality of the system and n is the number of particles, the off and off exponents. We compute the so-called orthonormal Gram-Schmidt vectors. So we do this periodic orthonormalization at each point of all these vectors. And so at each point in the phase space, we're looking at all directions in phase space, and we're saying how fast do those points diverge. Formalism here, we won't go through it in a lot of detail. We use symplectic integrator. This is called velocity delay. It's very common in molecular dynamic simulations. It turns out it's also quite good at dealing with variations of position and momentum, which is what we do in this case. So we cast velocity relay as velocity relay for the variations in the position and the momentum of all the particles. We write the vector matrix form of that, and then we figure out how to assemble the Jacobian for each time step. The Jacobian for each time step involves the two computations of the Hessian at the first time and the second time. This is the full either analytic or numerical Hessian. So for a big system, you can imagine the compute cost is at least n squared. So all of a sudden we've gone from a classical calculation, which is at least sort of order n log n, to something that is order n squared. And if you are someone who has ever done molecular dynamic simulations, you know that this is a big deal because now we can't scale to ridiculous system sizes anymore. In fact, we can't really scale the system sizes beyond what you could typically approach with quantum mechanics, and that's a problem if you want to do statistics on all these things. So, so that's that. We compute these every time step. We assemble them into the Kolmogorov-Sinai entropy, which has been shown to relate, which is the dynamical entropy that we're going to measure. And then we compute subsystem vectors, and this is in this paper here, along with a paper in PNAS that defines how this is actually computed. But this is the key, and I'm going to tell you about that in just a second. Said this is relatively computationally complex. Storage goes as dn squared. The algorithm involves multiple QRs, multiple Hessian calculations, and you assemble all that together, and the limiting factor is generally the QR, as well as the matrix multiplication, which are quite large for even small systems. 1.4 million elements for just a 200 particle system, which is quite large. So when we actually do this, we get this assembly, and this is the change, or it's actually the time domain signal of the Kolmogorov-Sinai entropy for four different things. We have the total Kolmogorov-Sinai entropy, that of the assembling system, that of the hypothetical non-assembling system, and one of the bath. And what's really cool about this is that you have the total, the non-assembling system, and the bath, and you look at the change in the Kolmogorov-Sinai entropy as a function of time, and they all pretty much lay right on top of each other. This difference here is actually a finite size effect. If you then look at the Kolmogorov-Sinai entropy of the system particles, those particles that had the dynamics that led to assembly, particles that actually came together, they have this completely different response, right? That's quite interesting. This was like a year and a half's worth of work to get to this point in my postdoc, and it was like this eureka moment where we all went out for beers later, it was quite fun. And as it turns out, that Kolmogorov-Sinai entropy of characterizing the dynamics of the assembly itself fully characterizes the dissipation statistically. So if you look, this is actually the fluctuation in the Kolmogorov-Sinai entropy of the assembling system as a function of time for 3 different perturbation strengths. And if you look at that, these are arbitrary units. They actually lay right on top of each other. If you look at that as the difference in the variation of the temperature of the bath and therefore the kinetic energy of the bath, these are right on top of each other within some degree of uncertainty. And so you have fully characterized the amount of dissipation and therefore the final assembled structure of the non-equilibrium self-assembly simply by measuring something that is specific to the assembling particles themselves. And that's quite powerful if what you want to do is come up with an entropy and sort of a non-equilibrium thermodynamics that characterizes self-assembly. Okay, so that's that story. The big thing here, and the thing that led us to actually take this very seriously from a computational standpoint, to say nothing of the fact that these are just very big matrices and you're doing a lot of big things to them. And so we wrote 2 codes. We wrote a distributed memory version of this classic HPC cluster stuff in MPI, as well as a CUDA version of this, which is what we spent actually most of the time on, which has interesting memory issues, similar to what we're doing in deep learning these days. But what this involves, this whole process of splitting up. So here we have C. C is the group that you're splitting the exponents in. And so what you're doing is you're extracting the position and momenta components of the Jacobian that you've assembled at each time step and reformulating that into new matrices. So this is pretty hardcore just matrix manipulation. And if you think about a molecular dynamics simulation where all the particles are all over the place at all different times, and you have a static group of particles that you always want to understand what their dynamics are, this becomes a random totally random scatter-gather all-to-all calculation on a computer. And for those of you that are more computationally inclined, you know that that's sort of a death trap in both distributed memory and GPU computing. because particles are ordered in memory, but they're random in real space. So these are completely random reads and writes. And how do we solve this? Well, I actually wrote to the ICL group, Jack Dungara's group at the University of Tennessee, who is sort of the grandfather of all this dense linear algebra stuff. And I said, look, we have this problem. I can't figure out how to solve it and make this fast. And after a couple of emails back and forth, he wrote back to me and he said, good luck. There's no solution. So how do we actually do this? I won't go through the code, but what we actually really do is just be constantly vigilant about a number of things about the configuration of the system. So where are the groups? In memory and in space. How do they relate to each other? Are they contiguous in memory? Can you copy big blocks? So you do like manual prefetching. Can you look at how many particles in my group are actually contiguous in memory, go and prefetch all that information, store it in a new matrix, and then go on to the next one? And to do this dynamically. Or, alternatively, can we do something clever about reorienting the Jacobian every single time, at every time step or after some number of time steps? And then lastly, can I take advantage of advances in architecture, like dynamic parallelism and CUDA, which is now old, but at the time was being developed, that let us do this. So you see a lot of all the functions that are in this code, which is quite a significant code, that look a lot like this, where we're doing a whole bunch of really sort of awful work just going through the lists of all the relationships between all the particles in the system, looking for, figuring out if they're contiguous in memory, storing those off, and then just doing this over and over and over again, because even all of that overhead, while it's very latency bound, is much, much better than fully random scatter gathers. Okay, so at this point I've talked to you for about 20 minutes about something that has nothing to do with artificial intelligence in medicine. So the question is, why did I get into medicine again? And A, it's interesting. But B, when I came to Mount Sinai and started working on some algorithms, I saw a number of opportunities for the kinds of tools that are being used every day by physicians, and by extension, the research community and deep learning and other things that could benefit from a lot of the kinds of more hardcore optimizations that we try to do that are very problem specific. So here's a medical image. I got pretty interested in this. I got pretty interested in the idea of actually quantitating something about somebody's tumor that was really difficult to differentiate from its surroundings, that had all sorts of other random stuff in it. And the first code I ever wrote at Mount Sinai in the area of computational image analysis had nothing to do with leaf throwing. I hadn't even done anything in that area yet. And what it was a sort of expert-driven understanding of how to segment an image using a clustering technique. And the one that we sort of focused in on was mean shift segmentation. Mean shift is conceptually simple. It's also theoretically simple. If you think about it, you just start, if you're just in a Cartesian plane, you just start with a distribution of points. You're looking for the catchment basins of the density in that Cartesian space. And so you start by just distributing a whole bunch of random points, and you look, and you draw a circle, and you compute the centroid in Rn. And then you compute some vector that goes to the new centroid of that data, and you just do this over and over and over again until all the points that you initially distributed on that plane converge. Okay. So that's what all that text says. It's actually really easy to say. It's equally easy to understand if you just look at some data like this. So here's an example. This is not my data, and I neglected to put the citation in there, so my apologies. But very simple. If you just look at this on the left and you say, okay, well, where are my clusters? It wouldn't be very hard to figure out that there are 7 of them here, depending on the parameterization of the mean shift that you use. And that's what you get. Conceptually, this looks like a catchment basin finding technique in the density. So what you do is you just sum all those different things together. The formalism here is really very straightforward. In the interest of time, I'm not going to go through it, but it's very easy to cast this as a very high-dimensional problem as opposed to all of these individual points on in the space, and compute a single mean shift vector in the high-dimensional phase space of the system, and use information other than density in your construction of mean shift. So you can use spatial and range distance functions. So we actually use information not only spatially, but also in terms of the color. And in our case, in medical imaging, color means intensity. We have a single channel, not 3, and do this iteratively. So again, why did I get into medical imaging? Well, if you think about that problem from the standpoint of a lot of random points in space, all of which have a neighborhood that is completely independent, random in time as you iterate through the procedure, that again looks a lot like a totally random scatter-gather memory optimization problem in the computational implementation. And although you get away with it in this case because the problem is relatively small and you can do this in shared memory on a single node, if you actually want to make this fast in 3D, which is what we care about, this is a disaster on a CPU. And there are nice optimization techniques that we can use to turn that into a relatively fast GPU-enabled 3D segmentation. The cool thing about this is just this massive dimensionality reduction. You haven't specified, it's not like k-means, you haven't specified your number of clusters ahead of a priori. And depending on the heterogeneity and how circumscribed the object that you were interested in segmenting is from this, from a given scan, here's a big meningioma that's very pretty homogeneous and very well circumscribed in the image. It's very easy to just segment that directly out as one of the components of the clustering that you do. What does this look like? We're going to talk a little bit more about this at 10 or so in the second talk. But this is really quite conceptually straightforward. All of the sort of magic lives in here in cluster labels, but from an organizational standpoint and how you put this together practically, we start with DICOM data. We move that into an ICK object of some kind. We'll talk about what that looks like. That usually goes directly into a NumPy array. We use 8-bit images typically, and we do these kinds of calculations for a number of reasons, mostly performance. Generate a 2D axial slice, or many 2D axial slices, or in the case of 3D, keep it as a 3D volume, compute the cluster labels, compute a mask, write that back down into a simple ITK image object, and then write it back out to disk where it can be used by a physician somewhere. There's a couple of missing steps in here about how you get from a mask or simple ITK mask to a 3D object. But there are many techniques for doing that. Probably most people are familiar with them. Marching cubes is one of them. Okay, so that was sort of the computational part of the talk. But we still have this issue which relates back to the title. I think showed you at least 3 different, very different kinds of simulations that we've done, and then the extension of those simulations to a computational problem in medicine for expert-driven image segmentation. But I haven't actually really defined what simulation in medicine means. And that's for a reason, because there isn't a strong consensus on what the word simulation in medicine means. If you ask different people, they're going to give you different answers to that problem. Coming from a computational chemistry or physics background, I tend to think about a simulation as something generally physics-based, generally where I have conservation laws, generally where I have some kind of time marching. So you could think about structural mechanics of the body, kinesiology, et cetera, as being something that would maybe fit into the idea of what a simulation is. But in fact, if you go to, in radiology or neurosurgery, where I said, or in many other fields that use this term, they really mean a lot of different things. So I'll try to tell you about, I'm going to give you now a whole bunch of examples to finish out the talk. That really look at all the different applications of what simulation means that we actually deal with on a daily basis. So a couple of these, I've split these into sort of 3 categories. I'm going to focus on medical modeling. One of the parts of my group that I run at Sinai is a big prototyping facility. So we do all sorts of medical modeling, not just all these cool computational tools. We actually get the results of these computational tools into the hands of patients, so I'll tell you about that. What I won't tell you about is what the rest of the whole day and really yesterday was about, which is more clinical decision support, et cetera, within the context of artificial intelligence. And we'll get there, obviously, by the end of the day. The last thing I wanted to mention before we actually jump into all these applications is the other way that simulation in medicine is typically used, and that is training in the spirit of flight simulation. This is a very popular analogy. It's certainly popular with the neurosurgeons that I work with. It's actually popular with me too. It's a good analogy. But given that this is an imaging symposium, I left this off. However, I do think it's sort of a fantastically interesting statistical question. How you demonstrate efficacy of a simulation tool for training in something as complicated as an open neurosurgical procedure is just a question that we haven't really answered yet. In fact, no, I don't think anyone has. We spent actually quite a lot of time trying to figure out what proxy measures we can use between the simulation and the actual outcome of a surgery to try to link up how you measure skill and how that translates into outcome for patients that might use the flight simulator. when you think about this in the context of flight simulation, we all assume that all of our pilots, certainly my pilot on Saturday when I fly back to New York, has spent lots of time in a flight simulator. I wouldn't want to get in a plane if someone hadn't done that. But why is that? Is it because we know that people who haven't had flight simulation crash a lot of planes? No, that's not true. So even in the context of something that's very well established that we all believe, it's sometimes difficult to really understand what the statistical basis is and the justification is for the tremendous expense of all of the simulation a priori. So it's a really interesting question that can be debated at long length. We use medical modeling. It's the section I'm going to talk about now. It's all nice and visual for the rest of the talk. For really three things and a fourth. The fourth I won't talk about. We use it for patient engagement. We use it to actually communicate with patients and to talk with them. We use it for surgical planning. And we also use it for training, but not in the spirit of the flight simulation that I talked about before. We actually have a whole group that primarily does entrepreneurial activities, and most of those are confidential and sort of beyond the scope of this talk, but I just wanted to include it to make sure that, once you understand how to do modeling, it's quite a straight throw to understanding how to build devices and test those. So, as always, we start with image analysis. Typical pipeline within all the medical modeling we do is very straightforward. We start with imaging, we do some kind of registration, and then we feed that into one of two different things, either some kind of volume rendering or some kind of large-scale visualization of that data, structural segmentation, and then creation of poly data that goes into the visualizers or into other things. Depending on the case, depending on the need, we do 3D printing in many cases. And then all of that information, structural segmentation information as well as volume rendering information and the registrations, make it into a number of other things that we do. Those include clinical studies. There's lots of good reasons why you would want to know the size and shape and statistics of objects that you segment. And then into clinical care. So virtual reality, augmented reality, heads-up display in the OR, surgical navigation, et cetera, which I'll show you a little bit about. Image registration, I'm sure everyone is familiar with, but just in case you're not. Two modes, MRI, CT, taken on different scanners at different times. We're interested in understanding the relationship between the information that is in the CT. In this case, it's mostly bony information, and the MR, all this nice soft tissue information. So we find a way to register those things together. The history of image-to-image registration is huge, 4 years old. It's probably just now getting to the point where deep learning is going to take all of it over and all that work is just going to be discarded, but nonetheless, the computational anatomy and that has been done over the years to really put this into use is quite impressive. So here's an example. This is Paul. Paul was nice enough to let us use all of his scans and sign a waiver signing all of his rights away. And you'll hear from Paul later. Paul had a particular type of tumor. This is the tumor down here. There's a whole bunch of other stuff in there. I actually showed you this slide before. And it's not really clear, even to me, from this scan, and I've worked on this case a lot, where the tumor begins, where the tumor ends. Is this normal? Is it not? We don't really know. Our goal, in this case, is to do something that looks like this. And that is, in the background, you have just a little bit of that MR, but overlaid, you have all of the relevant information that a surgeon or a patient might want to know for this case. You have an outline of the tumor here. I'm not going to tell you how I know that's where the tumor is, but this can be generated in one of many different ways, some of which we'll talk about today. You have an outline of cranial nerves, which have either been segmented manually or automatically through some other method. Bony anatomy, super easy from CT, barely have to do any work. Some relevant vasculature, in this case the carotid arteries, were very important to understand the relationship between those and the tumor. And these are just 2 slices of this. If you look carefully, you'll realize that when I made this slide, I actually misaligned the labels with the underlying scan, but that's just embarrassing for me. Okay, so how do we use this information? We use this for patients. So this is my chair, Dr. Betterson. This is a patient of his. And they're doing this. They're using all that data that's been segmented. In this case, they're using a volume rendering visualization together with information that has been generated from an expert-driven segmentation of the cranial nerves, as well as the tumor and blood vessels, injected into a quite straightforward visualizer. In this case, it's a company that makes this, but we also have our own in-house versions. And then taking the additional step, the thing everyone likes to do these days, and put on a set of VR goggles and go through this process of explaining exactly what's going to happen during the surgery, where their pathology is, what the issues are that are causing their symptoms, etc. We can take that data and we can consume it in any number of ways. If you do a really good job of segmenting and creating all of this structural information, then you can consume that any way you want. And one of the ways that we can consume it is we can take our 3D printers and we can throw them at the desk. This is actually the way the print comes out of the printer. It's a multicolor printer, single material but multicolor. You can see that the vessels sort of die off here because it's very thin structured. It's quite brittle. But in this case, this is the same case. We have the tumor in green. For some reason, we always print tumors in green. We have a bunch of nerves that have different colors. We have some vasculature here, and of course, we have the bony anatomy. This was actually given to the patient. Excuse me. This was actually given to the patient, along with a couple other models, not only preoperatively when they were planning the surgery and just explaining things, but also postoperatively. They actually took this home, or a version of this. So I'm going to show you a couple of videos here. This is Leslie Schlachter. She's the clinical wizard of our group. She actually is the one that communicates best with patients.
Right here now, right? Just this top centimeter right here, which is coming out, the cranial nerves come out of the brainstem. All these little itty bitty foramen is where they come out. They go to where they're supposed to go. Right? So ones that go through to the eyes come through here. The ones that go to the tongue come right through here. That's why we were telling you all those things, because all the cranial nerves have their own little home that they kind of spell into.
Mind if I just steal this first? So this is Paul. He was nice enough to, in a totally unprompted way, tell us about his experience with these technologies. That was Paul. Okay. So for surgeons, patients love this. It enables them to understand things. For surgeons, they obviously have a much more advanced understanding of what's going on. This is another video. I'm not going to use the sound on this one, or I don't need to. One of the things we do with this is communicating this information to surgeons in a way that they can actually use is sometimes quite difficult. And so we build these very small custom visualizers that take all the data that we generate from our segmentations. They're literally cross-platform binaries that are like a megabyte that I can literally email to a physician once we've made all of these things, and they can unzip, double-click, and just run on their desktop computer, whether they're on a Mac or a Windows machine or whatever they have. So this is a very straightforward, this is again, same case, a very straightforward visualization of the 12 or so structures that have been segmented in this case, and this is just a little computer that runs outside the ORs that we just throw these simulations on. The binary comes with it, so we can make improvements. It makes it a really easy way to get all this information in the hands of a surgeon without the expense of going through 3D printing or through some other kind of mechanics. Of course, we still do this in 3D printing. We find this to be particularly valuable in cases where there are haptic limitations to surgical access. So this is a case of well, I'm not going to pretend to understand the pathology here, but you have a tumor, again, printed in green, and the rest of the skull, and this is a case where they're going transnasally to get to this tumor, and the question is, do they have the margins that they want? So they'll actually go and actually do the surgery on this case to a certain level approximation, or at least put the endoscope through the nose and look at their margins. This is used not only preoperatively, but also intraoperatively. This is Dr. Creedy, who operated on this particular girl with a very severe scoliosis. I didn't know that scoliosis got this bad when I saw this case, but this is her spine preoperatively. It's basically a 90-degree bend. This is her before, her after, and then her with a 3D visualizer of the hardware that has been placed, as well as the rest of her bony anatomy. This was actually taken, wrapped in plastic, sterilized, taken to the OR, mounted next to the patient, and planned on as they open. Other cases are generally when, again, sort of structural margin issues that are really that are difficult to understand from the scans themselves. So we'll do this sort of gold standard expert-driven segmentation of these. In this case, it's just a hip joint. And the question was, can they leave enough healthy bone around to do procedure A or procedure B? Again, not a surgeon, I can't tell you about the details of the procedure, but what I can tell you is that they will be able to use this to actually make their drawings, look at it in real space, and say, okay, I'm comfortable with procedure A, which you can argue, although has not been shown statistically, to lead to decreased operative time due to improved knowledge before you get to the operating room. This is the last case that for surgeons we actually spend a lot of time doing stereotactic planning. This is called an SEEG procedure, or stereotactic electroencephalography. This is done by a number of our surgeons at one of our hospitals. And so this is a juvenile who has a number of leads placed. The purpose of this surgery is to understand epileptic foci in juvenile refractory epilepsy patients. And they take all these electrical recordings and they want to know exactly where that signal is coming from to be able to plan for either a resection or some kind of ablation or other kinds of techniques that they can have for killing bad circuits in the brain in patients with medically refractory epilepsy. So a sort of naive approach to that would be something like this, where we just throw it at a bunch of Atlas-based segmenters, and just volume render the electrodes. In our case, we could build a somewhat more clever version of our expert-driven segmentation to actually localize the electrodes directly with a point cloud. This is a straightforward process using code lines and a couple of PCAs to generate these kinds of models. Lastly, I just want to mention what we do for training. Again, I'm going to use the case of SEEG to tell you about this because I think it's the most advanced version of what we're doing for training within this context. We've built up a library of the cases that have been done this SEEG procedure. And what we tend to do is we'll go and we'll segment the skull, and then we'll segment a lot of the cortical vasculature. So if you're doing an SEEG procedure, you're of course going through the skull. You want to make sure you don't hit something that you really don't want to hit. And that involves a fairly complex array of things, including robotically assisted stereotactically registered for, navigation. I'll tell you what that looks like in a second, but here's an example of that print with just bone and some cortical vasculature that is segmented from an individual patient. And we have many of these. Over here we're actually basically going to go through the surgery right now, although you're not going to see the real version. This is a Mayfield clamp. You clamp the head, put it here. Again, in reality, of course, there'd be a patient behind that head, but in this case, it's just the head. This is called a ROSA robot. And there's a laser-based targeting system on the ROSA robot that registers the virtual space, the plan for the model, to real space. That process is quite straightforward. You basically take a bunch of points on the surface of the skull, and you compare those with points that you've selected on the model, and you register those two sets of point clouds together. There are many ways of doing that. It's an active research area. And then this robot serves as a targeting robot, basically. So what we have is you have this arm that goes, and you have a planned trajectory through the space, and you go, and that's exactly where you want to put your leads for the SEEG procedure, and so it lines it up perfectly for you, so you know exactly where those electrodes are going to go. This is actually me, and the reason I like showing this is just because it's the closest anyone's ever going to let me actually. So we've actually taken this around and actually used this to do a few different kinds of studies, as well as courses at various conferences for training in this procedure, as well as trying to actually quantify what the target localization error is, so that we can understand what the bounds of our certainty is in the placement of electrodes in this procedure. You can imagine this has significant other applications, but this is the one that we focused on. Like I said, we're actually going to go through this procedure on the model.
And we know that this is the same trajectory as we were before. So all we do now is we just go ahead and secure. This is actually it feels very good, like it's getting really good purchase.
And lastly, thread the electrode.
Just with my fingers, touch the bone.
Which means verify the location directly. This verification of target localization error is actually very difficult to do on real patients. So if you want to measure the relationship between your registration and the error and the uncertainty that you have in the electrode placement in the brain, the only quantifiable way to do that is to open the brain up and check, which would really defeat the purpose of doing this minimally invasive procedure. So this is what that looks like at the end. Another view of that. So, so that's what I wanted to show you. These are all the ways that we use simulation that aren't for artificial intelligence in medicine applications and clinical decision support. And I hope I've given you a flavor of what some of the things that you can do with these expert-driven segmentation tools, and even down the line, what you can do with all of those really fantastic kinds of deep learning tools that people are building now, that we've heard about yesterday and we'll continue to hear about today. So I want to thank a few people. The first part of the talk was in collaboration with my PhD advisor, Adrian Cooks, my very long time and current collaborator who's at UMass in dynamical systems theory, and then Yigal Slifer, who's my PhD postdoc advisor, and then my chair, Dr. Betterson, Ted Panoff, Eric, of course, and the host of students and other staff that actually execute these things on a daily basis for patients as the outcome of the computational work that we do. So with that, thank you very much for having me, and I'll be happy to take any questions.
So thank you very much for these really impressive talks. So I think we can take a few questions or comments. Because of a quick question. So you show us some mean shift segmentation to find the tumor. So I mean, if the tumor is really small, is it possible to apply the
It can be. There are generally two parameters that we tune, although there are others that you can play around with. Usually it's just what's the length scale, so how big are your spheres that you can feed in the centroid on, and then what's the color space that you're considering within the centroid calculation. So if you have a really heterogeneous tumor, you should probably include a lot more information in the color space. So you widen the color space parameterization of the method. If you have a very small tumor, you collapse the spatial parameterization of the method. So you can play around with it quite a lot. For very small, very heterogeneous tumors, it's still going to be hard. There are other methods that we might use to do that. And also, let's not forget that when you have very, very small tumors and you're just interested in one-shot modeling of the procedure, it's not very hard to just do this manually. So from just a purely practical consideration, that can be the right way to go sometimes.
So in addition to this color intensive, is that possible to incorporate something like a radiomics index, apply that to distinguish the difference?
Back into the segmentation, I mean, I don't know the answer to that. I don't know a really concrete answer to that. Certainly the direction from the segmentation to the radiomics is quite well established, and people do that all the time.
Yep.
Whether or not there's a feedback loop that is valuable back into the parameterization of the method, it's certainly not something I've ever done. And I'm not, within clustering, I'm not aware of anything like that, actually. It's an interesting idea. Yeah.
Thank you. Yes, sure.
So do you explain anything medical application of your non-experienced model?
Absolutely not. I have, all right, I will try. Let's see. No, I mean, what I was trying to relate is really the skill set that you learn in sort of computational physics on the compute side as being something that is something where there's a lot of room for excellent work in what people really know how to do in computational physics in medical disciplines. As I think I'll show you in the beginning of the next talk, a lot of the crux of it is that all the way down to the level of, in the research community, everyone's very advanced, but all the way down to the level of the clinic, there are all sorts of issues that prevent you from deploying these tools. Regulatory issues, just practical time issues. It's relatively expensive to do those registrations. It's relatively expensive for the engineering and person time to put in to do the segmentations on a case-by-case basis. There are a lot of these practical limitations that actually, I think, and we've made progress in this one tool and a few others, that sort of ordinary advancements in compute can actually lead to improvements in the care and the deployability of those tools. So maybe there isn't some dynamical entropy that we can and we've actually thought about things like that. For example, understanding uncertainty in tractography is an example of something that I would actually like to do at some point. We've talked about it a bit, but we haven't done it yet.
It's impressive. In your organization, do you use computer modeling simulation to evaluate surgical plans and find a good plan, or you go ahead and do the surgery?
Absolutely, yeah. So
how much is the computation requirement for this kind of work?
So, sort of the ordinary affine registration is probably the largest, or different registration in the case where that's required, although in the brain we don't really have that problem because everything sort of stays still. That's, some number of CPU hours. So it's not a quick shot. Someone has to plan for this ahead of time. The segmentation itself, depending on what's going on, if you have a very simple process where you can just use a expert-driven segmenter like a cluster or an active contour-based segmenter that I'll talk about in just a second, and then maybe skull and some very limited tubular vasculature that's quite easy to segment with expert-driven tools, with semi-automated tools, then that process can be only 15, 30 minutes. If you have a much more complicated situation where you have poor scan quality, need cranial nerves, need other kinds of structures, or especially the biggest bottleneck as far as I'm concerned is the fact that the people doing the segmentation are not usually the ones that have the anatomical and surgical knowledge. So that communication barrier exists and can lead to significant slowdowns in the process of actually generating models. Once the models are generated, yes, we use these in many ways every single day. So in a number of the physicians' practices at Mount Sinai, some kind of simulation, whether it's an industry platform, whether it's us, whether it's some combination, whether it's 3D printing or VR, AR, or interoperative navigation using heads-up display that's informed from the structures that we generate, all those things are done on a pretty daily basis.
Can I ask one more question?
Yeah.
About the software to do this, are there open source software?
Yeah.
Open?
Yeah, there's so many. Obviously the individual tools that are developed, we write those ourselves. And we just because it's a lot easier to just send someone a package and have them double click on it and have the simulation just run the way that you intended versus having someone, a surgeon especially who has very limited time, understanding how to boot up a simulation in an open source package. From a practical standpoint, we do write a lot of those things ourselves. However, there are hundreds of good volume rendering visualizers. There are hundreds of good underlying software tools that make it extremely easy to develop expert-driven segmentation tools. I mean, I'll show you a few of them in a second. But in terms of visualization, segmentation, even if you've never written a line of code, if you download Slicer, Seg3D2, ICT Snap, and a couple of others, you can do a lot of stuff yourself, assuming you have the time to do it.
Thank you. Okay. Thank you for this wonderful talk. I had a question about 3D printing. So, yeah. Can you actually choose 3D printing materials that are close to the biological properties kind of the anatomy you're looking at?
Yes, you can. We can't. So one can. So we have a few types of printers that are appropriate for this. Everything from like a desktop printer that you could buy and run at home, which actually they get a bad rap, but you can do multi-material work very cheaply with printers like that. I'm actually considering replacing a very expensive printer, which a bunch of those very soon. But the printers here, the multicolor stuff at reasonable costs there's a single material. We don't really have a choice. There's not much we can do about it. If you go from a $40,000 or $100,000 printer to $1 million printer, if you have that kind of cash lying around, you can get to the point of doing what are typically called multi-jet printers. And those multi-jet or polyjet printers can do multiple materials with tunable physical properties, all simultaneously, 7 or 8 different materials simultaneously. That's a very sort of brute force way to solve the problem. There are other ways to do it, and most of those involve making molds and using polyvinyl hydrogels or other kinds of things that you can injection mold to sort of, because with hydrogel you just sort of tune the chemistry and you can get pretty much anything that you want. So people make these really cool models of bone all the way through vasculature and actually bleeding models with hydrogel materials as well. So there's lots of options to the entire spectrum. It's just a question of how much money you want to throw at the problem.
Okay.
Okay, so I guess we can take a really quick break, and then let's thanks Anthony again for this wonderful talk. So we'll resume our talk. I guess we'll just start from 10:15. Okay, so 5 minutes. Okay, sounds good. Yeah. Okay.
Pretty cool. Thanks.
Okay. Yeah.
Hope it was fun.
So back in the second,
Yeah.
you'll be
I'll start.
Okay, and then
we'll transition over.
Transition over.
Yeah.
Okay. And you need to change the computer.
Oh, no, we don't need to change
it.
It's all.
Okay, I see.
Yeah.
Okay, that's cool.
So it might be a little complicated. We'll have to change the mics and stuff, but that should be okay.
Yeah. Hi. Also, I used to work when you were so young. I used to work for HPC, Jacoby, and Simple.
Okay.
And actually, I retired. Right now, I work as a job professor in Costa University, one of the biggest hospitals in southern China. Yeah, so we are thinking about doing something like this.
Okay.
Yeah, maybe I can contact you.
Absolutely. I'll write you down my contact. Do you have unfortunately I don't have any cards on me, but if you have one or something for me to write down,
maybe I can find your.
Yeah, it's easy to find me online.
Yeah. Okay.
But please do, please reach out.
Oh, okay. Because actually, the data volume in southern China is so big. I used to work at HAC for 25 years, but I find that one single hospital in China, the volume is equivalent to the whole HAC.
That's amazing.
For half year, it's amazing. Maybe we try to do something.
Yeah. Okay. Great. Nice to meet you.
Yeah. Maybe I let them talk to the leader of the team over there, and then you can invite you coming over.
That'd be great. Yeah, I'd love to.
Okay. Thank you. Thank you. Oh, this is like a morning.